stability analysis. And that gets coupled with frequency analysis, okay? Because it's easy to do. They're both basically modal analysis, that is, they're assuming a shape, and the analysis will give you which frequency things will vibrate at. And then we'll do buckling analysis, and the buckling analysis again usually is something resembling Euler analysis. The results are, and it has kind of the same shortcomings that Euler analysis does, and that is it's not all that great. Okay, or do I really? I mean, hopefully in this class I've installed a bit of distrust of just statics models, and I have lots more faith in statics models, statically determinate structures for stress, than I have in buckling or than I have in frequency analysis. And so these are things where we do these analysis, but oftentimes the real parts don't meet the way we modeled it, and those have even the difference between the way we model things and the way they're analyzed, or even have more pronounced effects on the results. So these are ones that I have very skeptical about. In fact, I've been skeptical enough in the past where people asked me for numbers and I said, no, I won't take your money, which for me is, kind of impossible. Too many years as a farmer, you always take money. So it's but anyway, I said, okay, I won't do the work because I don't believe they're answers. You can get a number, but I have absolutely no faith in the numbers at all. But with that said, we will at least talk about them and show you how the buckling analysis works. Today we're going to do buckling analysis. Next week we're going to do contact stresses. I have a bit more faith in contact stresses. For linear elastic material, contact stresses are a bit. They're actually it's actually a derivation of the static deformation analysis we've done already, and so as such, it has about the same error characteristics as the static analysis we've done already. I was going to start with contact stresses, but I'm not, so we're going to do buckling instead. Okay. So anyway, what I'm going to do actually ask you to do is I gave you a problem that I'm going to go play with, and I think I'll even hand it out. It's all up on Blackboard. I'm gonna have. I keep trying to. We realize this is our last quarter with Blackboard. No more Blackboard. Yes, Blackboard is going away. Going away. We're going away. Never to be seen again.
Canvas.
We're going to Canvas.
Oh, which is worse.
No. Canvas is better.
Blackboard is not improved.
No, we've gotten used to the inefficiencies that is Blackboard.
I realize I should probably have gotten used to the that sucks real bad. Blackboard, but
Yeah.
okay. So we're going to migrate to Canvas summer quarter. So everything in summer will be Canvas, and we're going to be using Canvas from then on. So, which actually I have to say that in many ways Canvas is better than Blackboard. So at least I've been forced to use it down at those other schools that, and it actually works better than Blackboard, which is somewhat scary. So okay, what we have is we have a couple of problems that we're going to do buckling. First of all, we have my favorite drawing, a pole, 40 feet tall, some piece of pipe here, 10-inch pipe, right, and a sign on it, okay, that's up there in space, right? It has some dimensions, and I told you it weighs 500 pounds. Okay. Doesn't that look like a nice sign? I realize it should say Sophie's office or Syra's office or Sheldon's office or Scott's office or
But Dr. Mean's office.
no, Dr. Mean's office. No. nobody would bother to put up a sign 40 feet tall for my office, right? So, okay. So anyway, what I want you to do is, first of all, we're going to solve the resonant frequencies, basically the frequency at which it wants to oscillate at, and the critical buckling load, that is basically how much we can load it for just the pole. We just have a 40-foot tall pole, okay? So that's not hard, is it? 40-foot tall pole? I'm picking these difficult modeling ones, you know. Right, okay, and then we'll do both solid and beam elements, and we can compare the results to theory on this, see what we do, and then we'll put the sign on and see if it changes things and how much and what it does, and do we believe any of the results?
No.
Depends.
See, you don't even have to run them and you already know the answer, right? But the problem is you gotta give something to the suits. They have to have something, otherwise they think you're not worth keeping around.
They gotta
right?
take credit.
They gotta take care. They gotta feel like their employees are getting work done, right? So
If they think you're not doing anything, they'll promote you to manager, you know.
Correct.
it's true. It's true. It is the Dilbert principle, right?
Are there any managers in here?
That's right. It is the. I don't dispute the Dilbert principle, right? And you are all of course familiar with the Dilbert principle. Incompetent individuals are promoted to management to keep them out of the productive workforce. Right, okay, that's the Dilbert principle, right? Okay, so let's, I'm gonna have SolidWorks here, and I'm gonna get some new part, right? And it's going to take me at least a day to remember how to use SolidWorks because it's been so long since the last time I used it. I think I rest my case there, right? Okay, so we have SolidWorks up here, sort of, chugging, kind of, maybe. Okay. And we're going to do some sort of pick a plane here, and I'll make actually, I think I'll pick the front plane, just because I can. I'll make a sketch, and I'm going to have a line. Okay. Okay. And then I'm going to dimension that line. Right, and I'm going to say that's what, 40 times 12. Okay. But that was easy, wasn't it? Get out of the sketch, and I think I'll go insert a weldment, structural member, go here and pick on some ANSI inch kind of thing. And I think I'm going to go pipe. Strong? Let's go strong. Why not? Size, 10 inch. Hey, why not? Okay. Something close. Groups, I want you. Okay, I have a pipe, 10-inch pipe, and I could say, ooh, okay. Now, of course, because you are actually given something with dimensions, you probably really want to actually go type them in, but because I'm lazy, you know, you can actually model the dimensions and make a custom weldment profile and all the other good things that you know how to do, because you've learned how to do all those fun things. Yes?
Professor, the inner diameter, is that given in those pre-made sizes?
Yep. Well, it's 10-inch pipe. What's the inner diameter going to be? Oh, this is the humorous crowd. I keep forgetting that, right? It's the humorous crowd. Well, in general, pipe is sized on.
Is it structural or is it
Just pipe.
for plumbing?
Just pipe. They're all the same. Pipe, you know, you.
Pipe standards?
Pipe is, well, you buy half-inch pipe, what do you get? If you buy three-quarter pipe, what do you get? You buy 1-inch pipe, what do you get? In general, pipe is specified on the ID. So sometime, many decades ago, if you bought half-inch pipe, it had an ID of 1/2 inch. And you bought three-quarter pipe, it had an ID of 3/4 inch. So if you bought 10-inch pipe, it'd be an ID of 10 inches. Now, reality hit them. Okay, first of all, when they first started making pipe, the steel wasn't very good. So the walls were pretty thin. So as the steel got better, they're going, now, wait a minute, now, we don't need to put so much steel in these anymore to get the same strength for holding the pressure that they need to hold. So what did they do? Well, you can either increase the ID or decrease the OD. But as a practical matter, you can't decrease the OD because all the threads and all the fittings and all the things that attach to the pipe are based on the OD. Right? So once you came up with the standard, right, was originally, okay, this is half-inch ID and we have some OD that we need to make the tooling out of. Okay, now we're stuck with it, and we've been stuck with it for, well over a century now, and we're gonna be stuck with it for many more centuries. Right? And you think we get away with it if we go to the metric system? Now, of course, it got even better. They said, oh, that thin wall pipe, sometimes we need pipe that holds higher pressure. So, we're gonna make the walls thicker. Well, we're gonna increase the ID or the OD. Or decrease the ID or increase the OD. If you make the wall thicker, you gotta do one or the other. Well, you gotta change the ID. Because if you change the OD, you're gonna have to make another whole set of tooling again. So the ODs are all the same, even though a half-inch pipe is not half-inch OD, right? It was originally designed to be half-inch. But the IDs are all over the place, depending on whether it's strong, it's regular, strong, or extra strong, which is Schedule 40, Schedule 80, or Schedule 120. So I have Schedule 80 pipe up here. I have no idea, other than the ID is probably smaller than 10 inches. And the OD is almost certainly bigger than 10 inches, because it was originally designed for being 10 inches. But hey, we're just demonstrating it. Is that a long rant on pipe sizes here today? Okay, so anyway, we're done with this. We're gonna go play with simulation here now. We're gonna do a new study, and now we're gonna go do something like buckling. Okay, we can either do frequency or buckling, doesn't really matter. Let's do buckling here. Now we can do buckling, and we're gonna say buckling. We say okay, chugs around. It's pretty happy here. We're gonna pick a material on this, right? We're gonna apply a material. We are gonna apply material. And of course, it doesn't really matter what material it is because it's going to be a steel. All we really care about is what the E is. Any of the steels will give us the exact same results because the modulus is essentially the same for any of them. So, and then we're going to do some fixtures, and of course, this is an easy one to fix because, hey, we're just going to fix the bottom down here, right? It's a cantilever. Do I make them any easier for you? Can I make them any easier at all? But let's see. We had to draw a line. We had to dimension it. Okay. So sorry, I'm bad today, and now we're going to put a force on it. And you're going, well, okay, I want it to buckle. So if it's going to buckle, how does it have to be loaded? It has to be loaded in compression. Yeah, so I'm going to put a force on it. Okay, that's fine. So let's go put force. Right. And I'm going to put a force right here at the top. And I need a direction. And so I think I'll pick a plane, like the top plane, and I'll say that I'm out of the plane. Okay, and I'll make the arrow really big. And it looks like it's going up, which I don't really like, so I want it to go the other way. There we go. Doesn't that look good? Okay. And it looks like I have a pound on it, and I'm just going to leave it at a pound. Go. Okay. That's fine. And then I'm going to go, just because I'm going to go back to my fixtures here and edit the definition again because I forgot to make everything really big. So now I got big symbols. Right? We like that? So I got a whopping pound on it. And I hate to tell you this, but this is oftentimes what we actually do. We go put a pound on it. Okay? And then we go, let's see if this will run. We can mesh this guy up. And it gives us beams there. We can run the study. Okay? And it gives us a amperes. That's an interesting discussion there. Amplitude really is amplitude, and I'm going to try to grab the results here, if I can grab the results, and come on, drag out here. There we go. Okay. Okay. So this was the thing, the results I got up here. I got a thing that said, oh, it's got an amplitude basically 1.49, which means it's deforming 1.49 inches, probably what it's doing. We have a mode shape 1. We have a load factor of 65,795. Okay. 65,795. Now, what the devil is a load factor? Yeah, basically, it's, I think I would not disagree. It's with what Sheldon said. It's how much we could push on it, how much more we could push on it until it buckled. Right? Okay. So, and right now it says we could push on it by a factor of 65,790. Right, 65,795, which means, and since we are pushing on it with a load of 1 pound, it means we would expect it to buckle at a load of 65,795 pounds. Absolutely. And we can do, just to make sure that we're interpreting this correctly, let's do something really radical here. Let's change our force. And instead of making it 1 pound, let's make it, what, 1,000 pounds? How about 10,000 pounds? Okay. Yeah. Put my truck up there. Okay, and what do I see now? I get this over here looks exactly the same. In fact, everything looks about exactly the same, except my load factor is now 6.5795, which basically what it is that I can increase the load by 6.57 times, and since I put 10,000 pounds on it, 10,000 times 6.59 is going to give me 65,000 pounds, which is right where I was at the beginning. Okay. Now shoot, let's see, I've been talking here for what? Well, 25 minutes? Okay. Not that anybody's keeping score here, right? But, okay, so we got, So that's buckling. Now, what are these mode shape things? Right? What are these mode shape things? Well, it winds up, of course, that if we sort of spin this thing around and look at it, it's bending. And then let me see if I can't play with that thing. It's actually deforming out, right? And this is making what's known as a mode shape, right? It's a curved shape that it will get in the a way it is failing, a mode of failure. We can actually look. I don't know if this will let us look at the others. There are other mode shapes there. Let's see if we can't look at the other. Come on. Okay. Resolution, chart options. Let's see, where's the, I'm gonna have to remember where I put the mode shapes in here now. I'm not seeing the other, where they stuck the other mode shapes, so. There it is, define mode shape plot, come on. I'm still hunting for it. Settings maybe? Nope, I'm not finding where I can see the other modes. Where did they hide the other modes?
Is it normalized mode shape? Oh no, just.
Compare modes. I just want to see the other modes. I was hoping that the arrows would do it, but they don't. That's the amplitudes, fringe options, the chart options, settings, maybe settings? I don't think that's going to do it. No, it's just in that part there. Maybe it is there.
Compare modes.
I tried compare modes, but I wasn't really happy with it. Yeah, 2 modes from list. There's only one, so okay. Well, it may actually not give me ones in here, so I may actually not give me ones in here. So.
Is it define mode shape maybe?
What's that?
Oh, never mind, that didn't work.
Actually, let me do the
Is it the user defined?
properties. Oh, that's because I didn't define any of them. That's why I didn't do. So let's go get 5 or 6 of them. So under the buckling, under the settings, let's go get some more modes. So under properties, you can say the number of modes, and that's why it can't find any, because I only defined one. Okay.
How many nodes?
Oh, I just picked a bunch of them. Okay. Now let's see if it. Oh, there's 2, and it doesn't. It looks exactly the same. And then if we get 3, see now we get a different mode shape. This is a different mode shape. Okay. And one of the things you'll notice is that while original, we have two mode shapes that are the same because one's in the X, Y. The thing is symmetrical. So there's my first mode shape there, right? And basically what it's trying to do is it's trying to make a big curve, right? It's trying to make a big curve in here. Okay, that's what it's trying to do. And when I do the second one over here, which they actually allow me to click at, right, it does the same thing, it's just doing it in a different plane. It's making a big curve here, just one big curve. Now, they don't really get interesting until we get to the third ones. Now, what is it trying to do? Well, now we're making an intermediate curve, right? This is the third mode, and if you notice, our safety factor, or our load factor, went from being 6.5 to some much larger number, right? Because while this is a failure mode that we're predicting, it's also a failure mode we're predicting at a much higher, right, a much higher load. Because these loads are the higher, they're less likely to constrain. Now, one of the ways you can eliminate, and this is true of all of the buckling issues, one of the ways you eliminate buckling problems is you reduce the modes. Like originally, what we had, if you remember, the original buckling thing was you had something like this. Right? The original buckling problem was specified like this, right? So F, right, where it's pin, right? That's the Euler buckling typically, and what you get is you get a mode that does this, right? Right? That's the mode you get, right? And when we're here, what are we doing? We're seeing a mode in these here. I'll go back to mode 2 or 1. These ones here, which mode are we seeing? Oh, that's wrong one, too far back. Sorry. We get the fun ones. What we're seeing up here is we're seeing, well, what happens if it's symmetrical here and we're just bending one side of it, right? There's an argument about that, right? Now, one of the ways to eliminate this mode is to go, let's brace it. Let's put something else in here. Okay. I mean, that eliminates that mode, right? Because what we've done is we've prevented that mode from happening in there. We've braced that mode out. This happens all the time in the building industry, right? When they're building structures up, what are they doing? They have columns. The columns, of course, want to buckle. What do? You put floors in, right? You've got floors, all kinds of other ways that are stopping the column from having that buckling mode. So now, what is your next buckling mode? Well, your next buckling mode is going to be one that's going to go like this, right? It's going to have because it can't move in and out of this spot right now, so there's going to be another one. Well, of course, it's going to be higher because the effective length has gotten shorter, right? And you can keep doing this, right? There are all more and more complex modes as we get higher. They're always up there. Right, so we can do the 2. There's the 3rd one. The 4th one will look almost the same because again it's out of plane. There's the 5th one. You see where we're even getting more complicated, and the 6th one. Right, they're just in different planes. We get these higher modes of buckling, and they're always there. Now, do we really care about them structurally? Typically not. Right. Typically you're dominated by the lowest mode. Right, but you can occasionally design your way out of them, right? Design your way past a low mode, and we don't like those buckling failures, right? Those buckling failures make your professor nervous. Okay? I mean, it wasn't that long ago they managed to have a buckling failure and killed a whole bunch of people, so that's not a good failure mode, right? Yeah, they had lots of them, and compressive loads can be nasty. There was a material science guy that years ago wrote a book saying materials don't really fail in compression, which is actually a true statement. Okay, that if you load them hydrostatically, which is real compression, they're on all 3 sides, right? They won't fail. You can crank them up as high as you go. I mean, at least they won't fail at anything we would consider reasonable pressures, right? I mean, obviously, if you get to neutron star or black hole densities, right? I mean, where the laws of physics get really weird, then things get different. But for anything that we would run into in sort of on the surface of the planet engineering, they don't fail progressively. What materials do is they get out of the way, which is why we say they fail in shear or they fail in buckling. And so doing this, what do? They go, hey, I don't like to be here. I'm going to be over there somewhere, right? And they'll get out of the way and let the structure fall down. So that's sort of the nature of these. Okay, that was easy, wasn't it? You think you can do that? Now, you think you can model that as a solid and do the same thing? Yeah, I think you actually can. I have faith. I have faith. You have faith. No faith. No faith. Okay. Okay, so we have to have faith in here. Got to have a little bit of faith, right? Just a little bit of faith. Okay, so I'm going to go ahead and go back to my simulation and go do a new study here. And instead of doing a buckling study, I'm going to do a frequency study. Okay? And say, okay. Okay, and now I get to do the whole thing again, right? I get to tell it what material it is. Oh, and I'm going to tell it it's steel, because I like steel. I know we're Boeing country, we make everything out of aluminum, but I like steel. We're going to fix some geometry down here at the bottom. All right, we're going to make the symbols really big, because we've done this before. Okay, and then we're going to put a load on the top. Okay. And we're going to put it on the top, up here, and we're going to define it from someplace convenient, like the top plane. And then we're going to assign it out of plane. And then we're going to make the arrow real big. And then we're going to tell it to go the other way. Okay. And then we're going to say that's good. Okay. Okay. And then we're going to mesh this thing up. And then we're going to say run the study. And what I get is just 1 pound, yeah. And I get this thing out here that says, okay, it's going to oscillate at, what?
1.7.
1.75 hertz. Okay. Which means that in a stiff wind, it's going to go back and forth, right? About a couple of seconds, right? 1, 2, 1, 2. So it's going to sway a little, but hey, it's a 40-foot pipe. You want to be up on top of the 40-foot pipe? Nobody here is in the flagpole sitting.
Harvey Danger.
What's that?
Harvey Danger.
Harvey Danger? Not familiar, sorry. Missed my hey. So again, we have, we'll look at different modes, and we can look at different modes. This mode is a 1.75 hertz, and of course I'm going to get another one that's out of plane. That's going to be doing the same thing, 1.75 hertz, right? There's one in one plane and there's one in the other plane, and they're at the same frequency because it's a bloody pipe, right? I mean, they separate out the two planes because there are, if it's not a symmetric section, if it's like a piece of rectangular tubing, which is what I should have used, something to make life interesting, right? They'd have been different frequencies. Okay? Right? We've been slightly different frequencies. I'll have to go back and do that. And then we can go look at the higher modes, right? And the higher modes are now up at 10 hertz, right? So there's 11 hertz frequency mode where it's oscillating back and forth, right?
So that means it's going back and forth 11 times in 1 second?
Yep. Yep. Now, it's not oscillating very much, right? The higher frequency ones are typically the amplitude of them much smaller, right? As a rule, those are actually, but that's another harmonic mode that's in there, right? And there's basically an infinite number of them, right? And there's the fifth mode, which is up at 30 hertz, right? 30 hertz, right? So, and of course there's this, okay, so that's the 5 that it did. Let's go It's actually a good question back there. I'm going to go back to my model here, and I'm going to go pick on the this pipe here, and go. Come on. I want the. Oh, come on.
If you go to the sketch,
I have to go to the weldment, or is it on the sketch?
if you right click under the pipe, you expand the pipe, that's sketch says.
Options. Cancel. It's not down here. It's not letting me edit it. And I'm not sure if I need to edit. Well, heck, I'll just blow it away. Why are you not cooperating?
Are you supposed to edit the pipe underneath that?
I tried, but it didn't like let me.
The sketch, what if you right click the sketch, because that's what.
Yeah, I can't, I can show it and I can zoom to it, but it doesn't let me do anything with it, right? So, well, let me see if what happens if I hit delete. Doesn't like that either. Cancel. That's not very nice of it to not let me edit the thing. I think I must be in a strange mode. Are you in the same mode that I'm in? Yeah, you can't do anything with it, right? So, okay, well, that's annoying. So it's not letting me.
We're going to features and edit feature.
Oh, that's right. Okay, you're right. I was in the
Yep.
wrong one. There, is that gonna help?
Maybe. Sure.
Doesn't seem to help when you're under that as well. Yeah, it's not letting me. I really wanted to change it to a different cross section, so we could go play with it at some different. But it's not letting me. I can't even. I don't think I can even delete it. It's not letting me even delete it, which is really not very nice of it.
Yes, you can. Yes, you can delete it.
You can delete it?
Yeah, you can delete it.
Different, right click?
Just
Right
delete
click?
it.
I think it has to be right click.
Yeah, it's not.
No,
Alright.
just click on it and delete button. So if you
I
just
can
go to insert weldment and you add a new one, does that just?
Yeah, well, I could probably do that, but then it'd get rid of the old one. I can pick this.
Yeah, you can hide that one and then just use the sketch again.
Yeah, okay. Certainly can use the prior sketch, right?
Yeah.
And then insert a new section.
Yeah.
And then I'll have to. Let's go for some tubing rectangular. And what size do we want? Let's go for something like how about 10 by 5? That sound like a nice one? 5/16 wall. That's a fine size there. Groups. I just want you. Okay. And we'll take that. Okay, and now I have 2 of them here. And ooh, now it lets me edit it. Okay, well, that's fine. Now lets me delete it. Yes. Okay. Now I got the tube. I can go back to the buckling now. And yeah, I think it's all good. I need some applied material, right? We'll do I just made it a rectangular tube is all I did. All right, and okay. I think it's just, no, wrong button. I think I just need to recalculate the joints. Okay, calculate. Okay, there we go. Okay. So I don't know why you're unhappy. Okay, you look fine. Okay, yeah, you're fine. Okay. And the force it didn't like. Come on. Force. Oops. Yeah. Okay. And get rid of you. Yeah. Why are you not happy? Okay. You're perfectly happy. You got, I need a joint. That's right. Want to pick on you and want to pick on you. Likes joints, other direction, right? And the symbol setting needs to be big because we're doing this. So, okay, we're just playing with this. Okay. So now we can make the mesh this guy and then run the study. Okay. And if we go to mode shape 1, we still have this. Now we notice my load factor is down about 11,000 pounds, right? 11.5 for this particular one, right? I got the same mode, but when I go to the other direction, what's going to happen is I have to look at the other plane, right, over here. I still have the same mode shape, but now my load has gone up to 34,000 pounds. What's happening is because it's asymmetric, it wants to bend the same fundamental shapes, right? But it takes a lot more to fail in one direction than it does the other direction. So it's buckling in the skinny direction, right at 11,000 pounds, or predicting that, and it's buckling in the wider direction at the 30,000 pounds, right? And we'll see that same behavior the rest of the way up, right? Here we have one that's the third mode, and let's go to the fourth mode, just because it's going to be in one of these other planes, right? Oh, it's not deforming very much. Come on, they didn't give me any. That's because the scale's not very big. But come on, is it in one of those? There it is. There's the next mode up, right? See, and it's deforming at 100,000 pounds instead of at 30,000 pounds, and that's the mode that'll be in the skinny direction, but it's the more complex mode, and we'll just follow them on up now. There's the fourth one, right? It's almost at 30,000 pounds, right? And then there's a fifth one up there, which is probably in the other plane. Right, they go back and forth between the planes. There it is, and that's the one it's actually the thick direction, but it's a lower mode shape. It's because it's easier to bend it in the other one. And this is not. I wanted to do this just to have an asymmetric cross section, so you can say these mode shapes are going to be the shapes are basically similar to each other, but they're happening at different values if the cross section's asymmetric. When it's round, of course, what do? We get values that are all the same, right? Because it doesn't care, right? It's going the same way in both ways, right? Okay, and then if we do the frequency, analysis, which I'm going to have exactly the same problems, and it goes, oh, I'm so unhappy, you're so mean to me. Let me recalculate all the joints. Yeah, okay. Recalculate the joints. Yeah, I know. Let's see if I can't make the fixture here. Come on. I just want to edit that, right? Yes, I know you're unhappy. And that's because I want you to fix down there, right? Okay. So now you're happy. And I get you. And it's just because whenever you recalculate them, it doesn't know where it is. Right? And now it's happy. Should be happy. And we should be able to create the mesh. And then we run the study. Oh, you're going to say I didn't define a material. Okay. Steel. Okay, and we see we have one it's not showing in this view, but we'll pick the one of these other views. We're gonna have a fundamental mode, and this one's down at about a little under a hertz. Basically, it's at a hertz, right? So what's it gonna do? It's gonna oscillate back and forth in a second, right? So it's a 1 hertz oscillation in there. If we look at the next one up, right, it's gonna be in the other plane. So you wind up going back and forth between the planes. Here's the other one, and it's at 1.7 hertz, sort of close to where we were with that round tubing, right? Because the round tubing, the first one was about 1.7 hertz. And then if we keep going up, they're going to get higher, right? Come on. There's the third one, right? And now we're up at 6 hertz. Right, we're getting another oscillation where it's going back and forth from the top. And there's the fourth one, there's the fifth one. It's up at 17 hertz, and these will be really small. So that's all they got in the fifth one. The fourth one's going to be that other same shape in the other planes. So keep rolling around. So that's that second mode shape that we're getting there. Okay, so does that make a little more sense that we do? Now, can we do the same thing if it's a solid model? Yeah. Yeah, we just put a force on the top, see what it does, right? See if it does the same. Can you calculate the buckling strength of that from Euler buckling?
Can you compare two SolidWorks designs?
You're using a computer to compare a
Can the
computer.
computer compare?
There's a design results, design study thing in SolidWorks where they're designed to look at different variables, and in all honesty, I haven't played with it.